Arjan.
Thanks, Zach. So I'll be talking about Wildfire refugia here, and I would like to start with thanking my collaborators, Crystal Colden, Jim Lutz, and John Abatsoglu. And this work is sponsored by the Northwest Climate Science Center. And I am about half a year into the project, which will last 2 years. So I'll just talk about how far I have gotten so far. Let's see if this works here. So I wanted to start off with showing you that fire is pretty common in the Northwest. You can see here all the fire perimeters of the monitoring trends and burn severity data set from 1984 to 2014. And so you can see that there's lots of fires going on. But what you do need to realize if you see these perimeters that the fire is not equal in that perimeter. So if we zoom into one of these fires, there is a lot of different severities within this fire. So this group, the MTBS group, classifies these different severities within these fires. And you can see that the red is like the high severity, and then we can go to yellow, which is moderate, and then blue low, and then the green, and that's where I'm interested in, is actually the areas that didn't burn within these fire perimeters. And this is actually the Carlton complex, which used to be the biggest fire ever recorded in Washington State. But I think this year we already have a bigger fire, so big fires. And then Crystal has shown, Crystal Colden shown at other places, for instance, Yosemite and Glacier, that these unburned areas, they vary and are sometimes pretty significant, from 37% in Yosemite to 14% in the Yukon-Charlie National Parks. And then, so we have unburned areas, but we have wildfire refugia, and they link together. But I wanted to sort of step back a little bit about what are refugia. And the talk we just saw was a very good example, because refugia are actually the definition from that comes from more from the retreat of land ice and deglaciation. And so refugia is defined as habitats where biota retreat to, persist in, and can potentially expand from under changing environmental conditions. And then wildfire refugia have been more recently defined as then locations where physical conditions decrease fire severity, allowing the persistence of fire-sensitive taxa or communities. And it really depends on what kind of species you look at, how these refugia would look like. You can think about butterflies, where we have a little patch which didn't burn at a given time, and it can persist there. But you can also think about old growth, where we have longer, where the fire didn't burn the whole forest for longer periods of time. So it really depends on what are you looking at. And so then these wildfire refugia, they can provide critical roles for the ecology of the forest or the landscape. So they can provide the refugia for the biota there during a fire, but then also after a wildfire, they can provide shelter. So thinking about wildlife, and then also they can provide a seed source for recolonizing burned areas. So what we want to do is we want to detect them, so we know where they are and how best to preserve these unburned islands or wildfire refugia, if you will. So, and if we can do that, we can maybe have a tool to improve the ecosystem resiliency for future disturbance, thinking about maybe more fire or climate change, where we have species distribution shifts. So, so this detection is already happening. MTBS is doing this, but as you can see here, in the blue, they have experts looking at every fire and sort of picking a threshold to separate the unburned from the burned, and also the low from the moderate severity, and so on. So that is a little bit subjective, you could say. And then they also just use one variable, which is normally the difference normalized burn ratio, which is a spectral index where they look before and after the fire and difference that, and then look at that threshold. But we think we could maybe use some more variables as well. So then my overall project objectives is to improve the detection of these unburned areas across the Northwest. And then I want to characterize these spatial patterns and then establish a whole database for all these unburned areas from 1984 to 2015. And then I want to relate the number and sizes of these unburned areas to a changing climate, seeing if there might be some patterns, if they are disappearing, or maybe we get even more of these unburned areas. But for today, I'll just talk about the first objective. So for my methods, I have about 821 field locations across 20 fires, and 565 are on forested and 265 are on non-forested land. And at these field locations, we did a composite burn index assessment. So we look at how severe is the forest burned by looking at all the different strata within the forest. And then we get a score from 0, which would be unburned, to 3, which would be severely burned. And we sort of place these plots in areas that were unburned or slightly burned to better like parse out the areas which are unburned. And then I use satellite data, and we have so we have the before the fire satellite data, and we have then the post after the fire satellite data, and then we also look at the difference between the two. And then there's another thing that we want to look at is that we want to look at the immediate, the satellite data immediately after the fire, but also a year after the fire. So we include all the effects of the fire. Sometimes trees will still die during the year after the fire. So we have a more complete idea of the effects. And then I'm using a whole bunch of spectral indices, and I'll be happy to talk to you, but I won't go into detail now about those, but I'll be happy to answer questions. And then I used topography, so elevation, slope, aspect, and then also a combination between slope and aspect. And then I used the land fire existing vegetation type to separate out some land cover, so I can build some models, so I'll show you that as well in a bit. So for the detection, I use classification trees, and then I'm running one classification tree for the forested areas, and then one classification tree for the non-forested areas. And I use a balanced design, so I have about equal numbers of unburned as burnt plots to generate the classification tree. And then I evaluate those by major fires and look at the overall accuracy, how accurate I was in predicting plots that I held out. And then once I established this classification tree, I apply that across the fires. So here is the classification tree of the forest, and I'll go a little bit through this forest, but through this classification tree. So first off, the DMBR, which is actually commonly used by the MTBS group as well, was the most important variable for the forest. And it's the DMBR which was used for 1 year after the fire. So if we look at that the difference, we use the satellite image which was captured 1 year after the fire. And so that parses out, and so maybe this is a bit hard to see, but we have here the unburned, and where there's here one, these are the burned areas. So when there's a large difference, we classify that as the burned. But then, if it didn't make this threshold, there's also, well, elevation is here a next step, and we can sort of see that low elevation forests which have a low NDVI at the after the fire, 1 year after the fire, can also be classified then as burned. So then we have this classification tree which we can then use for forests to classify the unburned versus the burned areas. And then this is for the non-forest classification tree. Yet again, we had the difference normalized burn ratio, which was the most important. But then the next split was actually looking more at the immediate satellite imagery. It was a spectral index, which is like right after the fire, and that makes sense because grass in a year later often will grow back and is still green, and maybe as green as it would be. But if you look immediately after the fire, you might get some extra accuracy. So then I applied this to the 2006 tripod fire, or the upper extent to it, and that's what you can see over here. And this is a false composite of the area, and in purple, or within this, that's where you can see sort of the highest, the most severe burn. And then this is how then the DMBR looks like, and the white is where, again, where it's really severe. And then what we then can see here in the red is where we apply the classification trees for both the forest and non-forest, and we can see then the unburned areas. So discussion. So we think this is a little bit has a little advantages over MTBS because it's automated. We don't need a user anymore picking threshold. And for this one fire, I showed an increased accuracy, but I want to run some more fires and see if this really holds up over more fires. And we think it's also a bit more objective. We really use plot data to sort of train the model and then get a good classification out. And, but I think there might be some more improvements, or I want to sort of test this at least going further. Maybe use a random forest technique or binomial regression. And then the other thing I want to look at spatial autocorrelation. Classification trees are normally pretty robust against spatial autocorrelation, but I still kind of want to have a look at that and see if that's true in my case too. And then the other thing is I've used the existing vegetation cover to split forest from non-forest, but that was based on the 2010 data, and the fires that I'm using are from 2006 to 2014, so so that might be a mismatch there, and maybe I can improve on that too. And then I might want to think also a little bit more about, like, I'm now just detecting the unburned, but maybe I also want to detect sort of areas that sort of didn't, had no transition, so still slightly burned, but we still have trees and we still have a seed source, so I might want to make a sort of a two-tiered classification system. And then there's some limitations. Of course, we use Landsat data, which is a 30 by 30 meter pixel, and I've been out in the field and I've seen like lots of little smaller patches, and especially in grassland, and that's probably like unburned patches which we are not capturing with this kind of data. So then going forward, I want to use these the classification techniques we developed to really make this database and apply that over the entire study domain here and see if there's any patterns evolving with climate. So as a summary, these unburned areas, are important and become wildfire refugia if there's a imported habitat there, like let's say a butterfly habitat, and it didn't burn, then we might have like a wildfire refugia. Or over a longer time, if it didn't burn over a longer time, then we might get old growth, which you could then call a wildfire refugia. And then we can use remote sensing and other data to detect these spatial patterns of these unburned islands. And then I've shown you here that we can improve on the MTBS data set, make it a bit more objective and slightly more accurate. And then, these unburned areas are important for for resource management to improve the landscape resiliencies for future disturbances to come. So, yeah.
Thank you, Arjan.
Sure.
We have plenty of time for questions. Does anybody have a question for Arjan?
A question from your work. Could you postulate or think that we could identify a priori potential refugia based on configuration of terrain, vegetation, and whatnot? And in fire suppression activities, where fire occurs, focus to protect those areas.
Yeah.
Give a chance for the ecosystem to recover faster. Instead of combating the fire regardless of what, focus in.
I think that's a good question, and that's probably a follow-up what we want to do once we've identified these unburned areas. We really want to look at, like, well, is there a topographic pattern? And maybe this is in some forest types and some other vegetation types that's not occurring, or even in some kind of fires where it really burns hot and it's really dry, it might not be occurring. But yeah, so that's something we really want to go towards, and then we can maybe also help managers, like, can we or we can manage the forest to make these barriers and sort of protect them in the future.
Consider that we spend $1 million a day only protecting the forests from fire protection this year. It would pay off to identify, triage the parts of forest hardly can expect to save, but saves as a refugia.
Right, because it's going to burn. Lots of people are showing that. So.
Would change the fire suppression strategies, but I think it would be critical that we do something with it, because what we are doing now is economically and nonsensical.
Yeah, and it would be good to bring the fire back into the system, and yeah.
Apologies if I missed this in the beginning, but could you just explain briefly how it's mapped currently, what the MTBS means?
Okay, so that's it's a group who's actually looking at fires bigger than 400 hectares, and maybe I didn't explain that very well. And they look at all these fires and use these perimeters, and then map all the severities within the fire, and they have done this since 1984. So this data set exists, but there are some issues with it, but it's a very valuable data set too, so yeah.
Anybody else? Questions for Arjan?
Okay, thanks.